Alright, so this is going to be a bit of a shorter stream. Um, like about an hour it's probably going to be. I want to focus mainly on one thing, and that's going to be fixing the refraction that we put in last time, because it doesn't seem to be working quite right. And if I have time left, I want to start on generating an, why does it say ABB, EVH of ABBs for a mesh. And the BVH is going to severely speed up our ray tracing, which is currently already getting pretty slow. I mean, 3 milliseconds for 64 triangles, that's not gonna cut it. Yeah, so let's get started. So I want to start by just sort of going through my code and recapping what the shader really does. So we have the vertex shader and the pixel shader. And the vertex shader calculates the screen space, clip space position, the world space normal texture coordinate. It also calculates the world space position and then creates a view vector going from the position in the world to the position of the camera in the world. And that's going to be our view vector. And when we load the normal and the view vector in our pixel shader, it normalizes them. Then we do some stuff with the time value that we load to do rotation of the triangles. Here we define simple triangle vertices. We give it a base position, and then as we actually do the ray tracing, we add an offset to all the triangles. Let's see. Here we calculate the Fresnel factor. Without the Fresnel factor, the Fresnel factor is basically how much should be reflected, how much should be refracted. Then we calculate a refraction factor, which seems to be broken. Then we do ray tracing. Then if we didn't hit anything, we sample the skybox. Then we sample the skybox for reflection. Then we combine everything based on the Fresnel factor, and then that gives our color for the water shader, which looks like this. So right here, it's just doing the refraction part, which seems to be broken. And then if we move down like this, you can see it reflecting like water. So the reason why I was thinking that it's really broken, well, it's also like super hot here right now because, you know, Europe, heat wave. As I was messing around with this position and nothing really seemed to happen. Like I put it at -10 and it did nothing because I don't use this variable. Ah. So our refraction might be correct after all. No, I do use this variable. You see? Yeah. Here we add the position of a triangle after we rotate it. And we put it like 10 units down. And I want to see what happens if we just put it at 0. How much that affects the picture. Yeah, they are more up, but now they should be like right on the water. But like -10, I feel like it should be more down. Like this is not, doesn't seem like 10 units to me. What happens if we do 100? Okay, that does put them down. Let's see. -20. Yeah, this just doesn't seem, it just looks weird. So let's do some research on refraction. Yeah, so basically our ray comes in and then we bend it based on what is it called again? Some index. The something something index. Refraction index, that's the word I'm looking for. But it does not seem to refract correctly. So, I'm thinking of how we can do some debugging with this. Let's change the refraction index based on time. Maybe that will help us. So we'll make it go between 1 and 2. Well, let's make it go a bit slower. And declare identifier t, because this should probably be time, right? Yeah, time. So this is the refraction index getting higher, I believe. It's actually really trippy. And then it will get lower. Until the rays basically becomes no. Is this making the refraction index higher? Well, goodbye worlds. So I think my code might be wrong. Let's double check this. So this will give a value between -1 and 1. This will boost it to -2 and 2. Oh, I need to times that 5f plus 5f, yeah. Don't want to have a negative refraction index. See, so now it's getting higher. And let's see what happens when it gets lower again. So come lower, 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 lower refraction index until we eventually hit an index of 1. Yeah, so now we're at the point where this would be air. Let's actually add just add a slider in our GUI so we can tweak that value a bit. So let me think how I can hack this in really quickly. Let's create a global in here. What's this? Yeah, sure. Global variable debug refraction index slider, and that's going to be 1 by default. Oh, I need to give the type float, obviously. And then in our main function, where I think we do some in-GUI stuff. Yeah, perfect. We can do an in-GUI slider float. And The minimum is going to be a half, a maximum one. Well, let's make it 2. Yeah, the rest I don't care about. We'll just use the defaults. Cool. And then in our rendering stuff, we can add a float or a constant buffer. And then we need some more padding because we always need it to be a multiple of 16 bytes. And we can just add this, we can just copy this stuff we added to the constant buffer in here and the constant buffer in there. Usually you wouldn't want to copy paste all this stuff, but we're prototyping, so we don't really care. Cool. Let's see. Somewhere I say dot time is something, so here we set our water constant buffer. And we're just going to set that global as the refraction index. Then from our bottom shader, we have the refraction index that we can stick in right here. And we use N2 everywhere for the refraction index. Cool, so now we have the slider. When it's set as 1, there is no refraction index, so it's going to behave as air. Now I can tweak the slider and it's going to change the refraction index. And last time I was wondering about this parameter where we pass the refraction index, where I basically took the reciprocal to simulate this. I'm not sure if I need this or this. Either one of the two I need. And all that does, I think, is just inverse which direction does what. So water is roughly at 1.33, a 1.33 refraction index. You know, this just seems wrong to me. Like I cannot see anything really. Let's check it out like this. This also seems a bit funky. Like, what is that water on the left edge doing? Like, what's happening to here? So what I'm thinking that might be going wrong is that we're just using this function completely incorrectly. And I was thinking of just writing our own refraction function and sort of dissect how it works. Perhaps figure out based on that what we need to do. So let's do some Google foo. Refraction vector. Snell's law. I think that's what we need. Let's see, lots of math. Yeah, this seems to be what we are looking for. Let's read this. Let a unit vector n, n1, n2, n3, where the length of n is 1. Any vector r could be decomposed into components with respect to n. See figure 1 at the bottom. Yeah, as in 3 vectors making up the one vector. So we got an x, y, and z component. This is probably math speak for that, but I don't speak fluent math. Or oh, this is parallel, this is perpendicular, I think. In the bottom, one parallel and the other normal to axis n respectively. Right, so if we dot the reflection vector along the normal, we get this scalar, and then we multiply it with that normal, we get this vector pointing up. And if you cross n with r, you get this vector. And if you cross this vector, which you can see right here, this vector with n, you get this vector. So you can sort of create tangents along the normal. The vectors t and I. What is t and I? So this equation is the same as that equation, but with a different letter. So is that one. Normal across t equals some constant n crossed with I. Right, so this is coming in, going out. Equation 4 combined with 5 and 6 yields t equals n dot t times n. So that's how much t is projected along n. Times some constant I minus the negative of the incoming vector along n. Taking norms in 7, since the vector n dot t times n is normal for the vector. This is a complicated way to describe this. Let's do something simpler. Let's just look for some C++ code that we can read and dissect. Yep. That's reflection. Or reflection, refraction. So like our vector should be bending pretty subtly. Ah, sine of theta 1 divided by the sine of theta 2 is n2 divided by n1. Um, 100% of light into the surface is reflected. In other words, when the angle of incident is greater than the critical angle, there isn't any refraction at all. This only happens though when the light ray passes from one medium to another medium with a lower index of refraction, such as in the case of water, air, diamond, air, glass, water interaction. This phenomenon is called total internal reflection. Right. And then basically they end up with this snippet of code. So let's see what they mean exactly with IOR. ETAI is the index of refraction of the medium the ray is in before entering the second medium. Yeah, and then ETAT or IOR is the index of refraction the medium is in is entering. Hmm. I really hate that the third parameter is just a question mark. If the angle between the entering ray I and surface normal size 1. Oh hey, Cookie is back. Hey Cookie. Like who names a parameter question mark? It's pretty ridiculous. If the angle between the entering ray I and the surface normal n is too great for a given refraction index question mark, the return value is 0. So that's that total inner reflection. If the angle between the entering ray I and the surface normal n is too great for a given refraction index. Yeah. So is this just the refraction index of how we're coming in? Lol, maybe they weren't even sure what it was. Yeah, I know, right? What does Jill SL have to say about it? Because I know they have a refract function as well. They must have. Yeah, they do. Let's see if their documentation is any better. ETA, the ratio of indices of refraction. And they have source code. Wow, that is way better. Reference to refraction factor R is calculated as. Oh, they even define how they calculate it. So let's just copy this and make our own GLSO refract. Let's see what parameters. We have I, N, and ETA. But that still doesn't specify how we should do the ratio. But we can look at that other article. Yeah, here they divide n1 by n2, so I think we should do the same. So it's going to be n1 over n2. K is, oh, this isn't actually, yeah, this is a constant. I can just say this. Yeah, this is just returning 0, total inner reflection. Let's also quote our sources in here. Always want to put the sources there, not only in case you want to open source it and you want to be nice about giving credits, also in case you find your bit of code, don't know how it works anymore, you can figure out what's going on. What's on the agenda for today? Not a lot, because I actually don't have a lot of time today, but I really want to stream. So we're just doing the refraction, and if we have some time left, we will start on the BVH for our ray tracing. Let's see. I think we're gonna get about the same. Yeah. So it might be that our refract function is actually correct. It just seemed incorrect to me. Or perhaps something stupid like our normal is not correct, which would be sort of ridiculous. Just in case, let me just print out the normal. That's normal and a 1. Yeah, it's green, so it is pointing up. It is correct. And then we have the negative over view vector, which actually points towards the surface. Like this is pointing towards Z. Is that correct? Is that pointing towards X? I thought X was the other direction. Is our view vector messed up? Let's output the position. Position in world space. It doesn't seem to like that. Oh, it's the resizing to a 0 pixel buffer bug. Let's see. So there's Z. Oh, I can't see X now. Let's render our terrain, which is this thing. Oh, I don't have world space position on that. Let me think. How can I figure out what is positive X? What if I just make this really big? Nope. That just gives me a hard edge. But that would mean that on the left side, yeah, like this is our natural way of looking at it. This right side is red, this side is not red. That side is blue, that side is not blue. So now our view vector should match that. Yeah, so if we look at that direction, yes, it's red, because that is the X direction, that's the Z direction. It's never showing any Y, because then we need to be looking from below like this. That seems to be correct. And there's not a whole lot more we can do to the refraction function. So I think it's just the refraction index, and it might just be looking weird to me. Perhaps because of the skybox that I just think is weird. Because it's infinite distance away, in theory. Sort of like that. Let's actually just make it black if we don't hit a triangle, see what that looks like. Yes, now we've got some really dark water. add some, just a lot of bending. Perhaps we can add a little beer slaw to sort of visualize distance. So I just have no idea what's going on with the distance. Did you have that debug window before? I don't remember that. Yeah, I had it the whole time. It's for my FPS and memory management stuff, and I just add more stuff to it as I need it. Yeah, let's see if we can add Beer's Law in there real quick. I remember that being fairly simple. Oh, that's all science. Oh, don't want any science. We're doing ray tracing. Ah, good old flip code. Yeah, Beer's Law, perfect. So, color of the material, which you can hard code, times some constant. Then we take exponent of those times transparency. Yeah, I think we just add this to our reflection color. So let's copy paste this and let's modify it. This is clearly coming from a CPU ray tracer. So let's set T, if we didn't hit anything, set it to like 100. Absorbance is let's make it blue with some constant, and then the distance is going to be negative t. Well, distance is t, but it needs negative distance. And I think we just take the exponent of that. I think we should just do this. Let's add our source. Always add your source. Need that sauce. It made things yellow. What? Should it be the inverse of the color? We made it yellow. It needs to be blue. That is also not the result we want. Oh, braces. So why is it the negative t? It shouldn't just be t. Yeah, and then I want to make them move up and down based on the time. Yeah, like that. So as they go deeper, they become more blue. I actually need to set the refraction index. So now they're in this weird, really blue liquid. Let's also sample the skybox again, or I was already doing that. Let's just not make it that far. Like this is definitely not the not the constant we want to use for water. Let's make the absorption way less. Still doesn't look very good, but sure. Let's make water the default refraction index in a second. It's really annoying to have to set it manually every time. Cool. Let's do that, and let's make it a bit fancier with the offset. Let's change the offset based on index. And it might not really like this. And this, yeah, like that. Now we got triangles moving differently based on where they are. Let's actually see if we can make a nice wavier pattern. Oh, I need to do this like that. Is pi defined in HLSL by default? No, let's see. Or do you just have to define it manually? Yeah, just define it manually. Let's see, how many digits can I remember? 3.14159265358, roughly. I think that's close. It's already past floating point limits, if I remember correctly. Yeah. Yeah, now we get a cool wave. You know what might be weird about it? It's the fact that these triangles go beyond our puddle. What happens if we just move them closer together? That might actually be the problem. Oh, that just is one direction. We can actually get rid of a lot of the triangles. Yes, now if they get up, they don't go, well, they still seem to go a bit past the puddle. Let's make our triangles smaller. Let's make like a quarter of the size. Just playing around a bit. Cool. Let's make it not go as deep. And let's see. They seem to be really close. Like still too far away from each other. Are they even still in the square? Yeah, they are. So now if they go up to the surface, they actually stay in a place where they can actually be. They're not like a kilometer that way in the water, even though there isn't any water there. Let's reduce this like wave. Make the wavy a bit more subtle. Now they're just really deep. And let's make them move up a bit more. What I think we really need to do to test this is get a mesh going of something like a pencil or some sort of cylinder that's like sticking in the water, and we can see it just bend the pencil or the cylinder. Can we do that right now? How am I gonna get a cylinder? Well, I'm thinking of a 3D mesh. How do I hard code something like a cylinder? Because it needs to go through the... Could even be a single quad, yeah. It also needs to go through the rasterization pipeline to be able to see it outside of the water. Should we just go start building a BVH for meshes? And then load meshes that we can render and also render underwater? Then we can just reuse our bunny. Our good friend, the bunny. He's been swimming this whole time, having a good time. Let's make him go visible in the water. We can even stretch our bunny to be like really long, and then he can be our pencil. Alright. So I don't really want to write a bunch of code for uploading meshes to the GPU to do brute forcing to then throw it away right away to do the BVH. I would prefer to just do the BVH. Let me explain first how BVH works, really basically. So what's happening right now is, let's say we have a bunch of triangles, and we can have like millions of these. And we have a ray. And let's say the ray is moving in like this. Well, not like that, like that. The Stanford straw. Yes, our bunny is going to be Stanford straw. So imagine this scenario. In this scenario, we have 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 triangles. To shoot this one ray, we are going to do 19 checks with a triangle to see if we hit any of them. And we must test all of them, because if we, for example, hit this one here below, but there was another triangle here, we need to continue testing because we don't know which one is the nearest. We need to test all triangles to know which one we actually hit. And as you can see in this case, the most common case, we're mostly missing triangles. And the ray is actually only going through like a small portion of our scene. So we're basically doing all this computation that's not going to end up giving us anything. So we can optimize this by doing the following. If we calculate this box around this half, and then a box around this half, we could first just test, do we hit the left box? If we don't hit the left box, we don't need to test any of the triangles in that box. Do we hit the right box? We do hit the right box. Let's test the triangles in the right box. Then we can go further with this. We can subdivide this box like this into multiple boxes like that. And then we can go even further. We can create more boxes like this. Let's add another, oh, that's actually more like that. And then we add another box here, maybe like this. And we add another box here. And for example, these could be in a box. And these could be in a box. This could be a box. Like that. And that could be a box. And what we can basically do is check, alright. We can even create like one big box around it. So first we test, do we hit anything as seen at all? Alright, we hit the scene. Do we hit the left side? We don't hit the left side. Alright, let's then just check the right side. Alright, do we hit the top half of the scene? Yes, we do hit the top half of the scene. Do we hit the bottom half of the scene? Yes, we do hit the bottom half of the scene. Alright, we need to test both those cases. Do we hit the left box? No. Do we hit the right box? Alright, let's test the right box. Let's test two triangles in there. Then, in the bottom boxes, do we hit the left box? Yes. Alright, test the triangles. Do we hit the right box? Yes, test the triangles. Now we'll only do 1, 2, 3, 4, 5 triangle checks. And let's see, that's 1, 2, 3, 4, 5, 6, 7 box checks. So that's 7 plus 5. That is, if I can do the math well live, that's 12 checks instead of the, was it 18 or 19 before? By doing this hierarchy of boxes, we can severely reduce the number of tests that we need to do as the number of triangle grows. And the way that translates is, instead of having to do a linear algorithm, we can do a logarithmic algorithm. So linear algorithm will roughly scale like this as the triangles go up. So as the triangles go up, time goes up. More triangles needs more time. If we do this hierarchy, it will go logarithmically. So with like really small triangle counts, there's a difference. It's not that big. But as the triangle count grows, it becomes like, it doesn't become that much larger. Well, this just goes off into space. If we build a really good BVH, it doesn't matter how many triangles we have anymore. If we double the number of triangles, it might be like a few percent slower. Just Just think about that. Doubling the triangle count, a few percent slower. That's just insane. Now there are a few things to this bounding hierarchy, bounding volume hierarchy. Let's add a new image. Let me draw a bunch of random triangles again. La 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 la, triangles, 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 triangles. So at some point, while we want to build this, we need to decide where will we place the boxes. In our last picture, I've sort of been placing them like what looks right, but how do we know what a good box is? So for example, what we can do is we can create a box like this, and then a box like this. But this doesn't really help, because with the left box, which actually should be covering this triangle as well, with the left box we just know, do we hit any of all these triangles except this one? And with the other box we just might as well just have tested the triangle. Or at some point we like doing weird boxes like this with like lots of overlap, where the box really overlaps. This is also not very great. So we need some sort of way of determining what a good bounding box is. And the thing we use for that is something called the surface area heuristic. I think that's how you spell it. Let me double check. Heuristic, right? Yeah, heuristic. And the surface area heuristic basically is as following. It's the number of triangles in the left box times area of left box plus number of triangles in the right box times the area of the right box. And this will give us some value. So it will basically look like this. We will end up with something like this. And what we can do is we can basically test a split point at every single triangle. So we can basically go like, all right, let's try making a box like that. Let's try making a box like that. Make it like that. Make it like that. Make it like that. Make it like that. Like go past every single triangle vertex to see what the best set of boxes would be. And then just find the one where this value is the lowest, this heuristic. The lower the value, the better the bounding volume hierarchy. Now, we can build our BVH offline and let it take like, I don't know, 3 weeks, and then it would be really good to test every single vertex. But in a lot of cases, you don't have the time to build these, and you need to build this in real time. For example, if you're doing animation. So what you would do instead is, if you have like 1,000,000 triangles, you just try 8 different positions on every axis, or perhaps even just the largest axis, and just figure out which is the best place to cut. And no matter where we cut, we can always generate a valid BVH. It's just that some are better than others. So our goal is to build a BVH using boxes. And right now the example is in 2D, but we're doing 3D, so we're going to be, instead of rectangles, we'll use 3D boxes, or the so-called axis-aligned bounding box, the AABB. And what I was talking about last time is I also want to try the what was it called? The axis aligned bounding something octahedral. Yeah, this octahedron. And this gets into like some more advanced shapes for encompassing geometry, which will allow us to do sort of a half pass. So this will be, on the right will be the final shape that goes around the triangles, which consists of these two triangles. But by just checking one of the triangles, we can already sort of do a rough check, like are we even close? And then we can do a finer check. And this will get rid of a lot of checks that we need to do. There's not a whole lot of time left. So let's just set up the most basic thing for generating a BVH, and let's actually go build that in our asset system. We'll just build a BVH for one mesh, just to keep it simple. Usually what you do is you have in a game like lots of static parts, and you would put those. You would just make one big bonding volume hierarchy out of those. And for all the meshes that move around, you would create a BVH per mesh and then put instances of those BVHs in an encompassing ruled BVH. So we're going to need a BVH of this mesh. Let's define some types. Let's do that at the top of the file, actually. I just need to extract this, let's see. So what I like to do is I like to call something called a C node or construction node. And basically we're going to build a BVH that's not very efficient memory layout wise, but it's just going to make it easy to build. And then we take that inefficient BVH and we optimize it into like the most efficient memory format that we can. So what does a node exist out of? Well, it's going to have a min for the ABB, so the smallest position in space, and it's going to have a max ABB. Let's see, there's a question about cookie. So you can store a local space for each mesh ahead of time, then only dive deeper into it if you cast against the largest bounding box. Really cool. Local space BVH. Yes. And what's even cooler is that you do not have to multiply the matrices, the vertices with your matrix. You only need to transform the ray to do all your camera transformation. So it's even like that, it's mathematically more efficient, which is just awesome. You do have to like do some fancy trickery like we did with transforming the normals, doing like the inverse of the transpose of the matrix. But it's far more efficient. Alright, so we have our min and max point. Then we need a child count. If the child count is going to be 0, if the child count is 0, then it means it is not a leaf node. If the child count is greater than 0, it means it is a leaf node and it has triangles. Now we need to think for a second how we're going to represent the triangles, because we need to also copy them around, I believe. Yeah, we'll just make an array of triangle indices. And we're just going to make it like really slow in the beginning, not optimized at all, and we'll optimize later. And what we'll also need is 2 children pointers. These need to be pointers. And what we can eventually do, but I know it's possible because I've done this many times, is at some point you can do this. That's actually going to be BPH. Let's actually call this BPH construction node. And then we can do the following, which is, let me think for a second. Yeah, you have child left and triangle index, and then you have child count. Let's actually call this try count, so we don't get confused with the different types of children. And this will, with this we can represent the same data, which fits, let's see, in 32 bytes, which means it only takes up half a cache line. Well, this structure is already 12 stops 24 plus 16 plus 4 plus 8, so that's 24 plus 24, that's 48. This is already 52 bytes. So we're going to be able to save already 20 bytes, but just writing our structure a bit differently. And what we can also do at some point is do the following, where we, instead of dividing in 2 each time, we can divide into 4 boxes, and we do it like the following. And I believe this is like, this stuff is more efficient on GPUs if you pack stuff like this. And we might have to pack it a little bit differently. And this might even become like 8 or 16, where we pack a lot of nodes together. But let's not worry about that. Let's comment this out because we're not doing that yet. Let's first construct our BVH. Well, let's set up our BVH because I need to go in like 5 minutes. And let's do an error code. Test build BVH. Let's actually just do void. We don't care about errors. It's a prototype. So our input is going to be an index buffer with an index count, and there's going to be parentheses, a vertex buffer with a vertex count. I'm going to build BVH from this, and we can actually calculate the triangle counts. And now I'm trying to remember what the maximum number of nodes is that we could possibly have. And I think it's double the triangle count minus 1. So let's just allocate that many nodes to build from. Malloc, so that's triangle count times 2 minus 1. Put that in braces. Oh, let's actually use our own malloc function, our own macro for that. Times size of the construction node. Let's also add a comment here. BVH construction nodes. Cool. So first of all, we can go build our root node. Which you're going to stick in the first node. We can then already set the node count to 1. So we need to calculate an ABV. So let's assume the first position is the minimum and the maximum, and then start looping at position 1. Hold on, I don't think I can just loop through the triangles. I think loop through the vertices. I think I have to loop through the triangles just to keep it consistent. So let's just say our default minimum is just really large, so we're pretty much guaranteed to overwrite this. And our maximum is just going to be really tiny. So we move along the triangle. Well, it's really annoying that at my day job I have to put braces on the same line, and now I just keep putting them in the wrong place. Alright, so we can do this. And here we'll load like that. To do let's actually get the minimum position of a triangle first. So and let's also calculate the maximum. Need to replace these with maximum functions. Right, so now we calculate an X-line bounding box around our mesh. And that's going to be the root node. Then we need to put all the triangles in this root node as well. And it might be more efficiently to do that before we do this. Might be like far more easy to follow. So the triangle count is easy. That's just the triangle count that we calculated before. Triangle indices. We're just gonna malloc it. Like that, and we'll just then copy over the indices. Oh, that's actually wrong. That needs to be also triangle count times 3. And then here we can actually just go through try counts times 3. And this is going to be root node triangle indices instead of just the index buffer. And we can keep the vertex buffer the same, because the vertices are gonna, we're not gonna modify the vertices at all, we're just gonna be messing around with the indices. Cool, so that's our root node. Root node, root node. Now we need to split hierarchically. Beautiful spelling there. So we need some sort of stack. I like just defining a stack element like this, which is going to be like we have a current element that we're working on. We can then create a stack of these and a stack index, so we know where in the stack we are. So the first thing that needs to happen is calculate the optimal split plane. Then we need to split. Then we need to check if we need to split. If we do not need to split, skip this node, pop one of the stack. Then we will split the nodes into two child nodes, generate bounding boxes for the child nodes, and then we will push the second child on the stack, and then make the first child our current element. I'm getting caught. Let me check real quick. It's calling me. Oh, I can come back in a minute. Yeah. Oh, and after we split them, we need to clean up the list of triangles in this node. Yeah, and then after we've done this, we have a very inefficient BVH. Then we'll optimize the BVH into a more memory and GPU friendly format, where we do all the fancy stuff with combining variables into one variable if we don't need them and all that jazz. I am going to end the stream right here though, because I have other things to do. I'm planning on streaming tomorrow because I got the whole week off, which is just awesome. Doesn't mean I can stream 24/7. I still have a lot of things to do this week, but I do have a lot more time than usual. So, yeah, I'll be streaming tomorrow. Probably somewhere in the afternoon for me. Yeah, because I can't do it in the evening because I got people coming over in the evening. Yeah, morning, afternoon should be good. And I can, yeah, let's do like a long stream tomorrow. Let's do like 4 or 5 hour stream or something. I'm feeling excited now that we started on the BVH. We're gonna make an awesome BVH. Then we're gonna try a couple different types of BVHs, perhaps, with like different ways of collapsing levels of nodes. And then we can do the axis-aligned bounding octahedron. Also the 7-sided axis-aligned bounding box. I just want to mess around with those. We can make a Stanford bunny that's going to be partially in the water, that's ray traced partially out of the water, which is rasterized. Tomorrow's going to be awesome. But that's it for now. I wish you all a very good evening or morning or afternoon, wherever you are. So yeah, bye.